Okay, so welcome back to the third part where we talk about, where we discuss the assumptions that we need for difference and differences. So again, the basic idea, as we saw in the randomized controls trials, we need kind of a treatment group and we need a control group. And these groups should be pretty much the same except for the treatment. So we have to make both groups comparable. And now the assumptions that we are going to discuss, those are pretty often the same in other parts of the literature for treatment effects. So for instance, in matching methods or the regression discontinuity design that we will discuss in the next lecture. So it's useful to keep these assumptions in mind anyway. Okay, the running example that we consider is again like a job training program. So as before, an X is a vector of observable characteristics, and something that we've seen already before is that we can write the average treatment effect on the treated in a particular time period as well, simply the average difference under treatment versus non-treatment in the treated group, where of course this thing cannot be observed because we cannot observe this in the treatment group. And by the law of iterated expectations, we can simply write the same thing, where on the inside, we also condition on a particular X variables. So kind of here on the inside, we make an apples to apples comparison where we, for instance, condition on people in the same industry. And then we average across all the X's. So that's kind of what we say here. So you see that this theta T of X is the average treatment effect on the treated in time period T for the subpopulation with a particular characteristic. So for instance, for all people that work in the IT sector. And as we said, if we want to generalize this to the whole population, we have to average this across all potential outcomes of X. So for instance, for everyone in the IT sector, for everyone in the construction sector, services, whatever, right? We average across all potential outcome of X. Okay, here we have a fundamental assumption. So this is so fundamental that people typically forget about it. So what we want is that we can see one and only one potential outcome for each member of the population. And very, very, very important is that my potential outcome is not allowed to affect your potential outcomes. So and this is kind of known as the stable unit treatment value, the SUTVA. And we have seen this thing here before. Like on the earlier slides. So you see that kind of like the observed outcome can be written as the outcome under treatment. So if okay, let's see, if the treatment indicator is 0, then what we get is actually the non-treated outcome. And if the treatment indicator is 1, this drops out and we see that we get the treated outcome. Okay, everything is all right here. Okay. Now, what is an example? Okay, in our running example with the job training, what would be a violation of the SUTVA assumption? Let's say the job training program is so large that so many people participate that for anyone that does not participate in the job training, they have now an easier time of finding a job because everyone else is actually taking the job training. So there's no competition in the labor market. And now the training happens to teach a certain skill. And after the people have done the job training, those people, the non-participants that had this skill before, they will now face higher competition after the job training, right? So kind of these people in none of the time periods, we can observe the potential outcome because the presence of the job training basically contaminates our potential outcomes. We would not we cannot observe what is the potential outcome of the non-participants in a world where the job training does not exist. We can never observe that because the job training itself has an impact on these people's outcomes. Okay, like an easy example, actually, when I want to run an experiment, when I say kind of I give a randomized subgroup of you the solution to the exercises, and I want to see what is the effect on the learning outcomes. And then you go and you simply distribute the solutions among the whole group. as the students would of course do, right? In that case, there's no way for me to observe any potential outcome without the treatment, meaning without the solutions. And the Sattva assumption would be violated because the treated, the potential outcome of the treated contaminates the potential outcome of the non-treated, because you distribute the solutions. Okay. The next assumption is called exogeneity. It's something that we have seen before. Exogeneity in the treatment effect literature really means that the conditioning variables should not itself be influenced by the treatment. Yeah, so kind of treated or non-treated X doesn't matter, it's only X. And why is this so important? Well, I mean, we have a treatment indicator and we have an outcome. So this thing varies. And we want to say that because of this thing, because of the variation in the treatment indicator, the variation in the outcome happens. Yeah, so kind of this is the causal source of the variation of this. Yeah. Now, if this change and this change induces also a change in the X variable, yeah, so then I cannot differentiate, I cannot kind of disentangle the change in the treatment indicator or the change in the X variable. Which of the two variations is now causing the variation in Y? This is the problem. If the treatment, the X variable is itself affected by the treatment, this introduces a confounding variable. So for instance, let's say X contains job satisfaction, which is probably affected by the job training, then exogeneity does not hold. And a tip here, by construction, if the X is invariant over time, it doesn't change over time, it's by definition exogenous, because if it doesn't change over time, it cannot be affected by the treatment, because the treatment turns on between period 0 and 1, and if X is simply constant, exogeneity, perfect. Okay, so this is exogeneity. So Sattva and exogeneity are standard assumptions in any method of causal inference. Yeah, so these are very basic. And the next one is a bit more specific to the difference and difference design. Yeah? So it's written like this here, kind of, it simply means, and here I think the name is pretty much telling it all, NEPT means no effect on the pre-treatment population. Yeah. So the treatment should not be anticipated. Yeah, so for instance, if I know that I'm unemployed today, but next month I start a job training, am I gonna look for a job? No, of course not, right? Next month I have a job training, and after that I'm gonna have a super well-paying job. Why would I get a job today? Yeah, so kind of because I know that there will be a treatment, I change my behavior today. Yeah. So therefore, you don't see the potential outcome without treatment anymore, because I anticipate treatment. So I don't know what would have been my potential outcome in a world where the job training did not exist. Yeah. So this gives us a problem. Anticipation of treatment is always a problem. And here we have what is called the common or the parallel trends assumption. And this is really, really important. This is basically what everyone is concerned about in difference and differences applications. And it really means that once you condition on X, means, for instance, if you look at the people in the same industry, the development in the treated group across time between period 0 and 1 should have been exactly the same as in the non-treated group. Yeah? So the trends are the same. It doesn't mean that the outcomes have to be the same. It simply means that kind of if there's, for instance, the economy is doing well, kind of like it moves up, they move up in parallel, yeah? In the treated and in the non-treated group. If, for instance, like the treated group benefits more from a growing economy, then it would look like this, right? And the spread would increase over time. I don't even manage to do this properly with my hands, but you know what I mean, no? Both go up, but one goes up larger. And this would violate the parallel trends assumption, because then you would attribute this higher potential in the treatment group for benefiting from economic growth to the treatment itself, and this would give you bias. Yeah, so the common trends assumption is really, really what you need. And again, as we've seen already in the randomized experiment, we have to condition on all the X variables such that the common trends assumption is plausible. Yeah? So for instance, if the IT people have benefit more from a growing economy than the construction guys, yeah, the trends would kind of be differential. So these people would go up in a different trend than these people. Therefore, you have to condition on the sector of employment. Yeah? So you compare the IT people that are treated with the IT people that are non-treated, and there you have parallel trends. Yeah? In the absence of treatment, right? So had there not been a treatment, they would have developed in exactly the same way. And now it turns out that these people, the treated, get a job training. So they move here, treatment takes place, they take off, the other ones move on. Yeah? And because they would have moved on in the same way in the treatment group, we can take the development in the non-treated group versus the development in the treated group, compare the difference, and this is going to be our treatment effect. So this is the difference in difference as idea. Yeah, violations of common trends. That's, I mean, we just gave an example, right? So you have to, for instance, control for the sector of last employment. I think that's also kind of here the example that I chose. Yeah, so common trends, super important. And here we have some examples from the literature. So this is actually taken from the Angrist and Pischke book. So what do we have here? We have a situation where you look at students that repeat the first grade. That's kind of the outcome variable. And the treatment was a change in the school year. So kind of I think they switched the start of the school year from, I don't know, the end of the year to the middle of the year, for instance, right? And that was done in pretty much all the regions in Germany, except for, of course, Bavaria. They always do their own thing. These are weird, weird people in Bavaria that I can tell you as a German. So they always do their own thing. And in this treatment group, the change in the start of the school year has induced a short school year for some of the students, right? The school year was shorter, so kind of like all the material had to be squeezed in less time. And this led to the sudden increase of people repeating the first grade. So what you see here is that everything moves nicely, more or less in parallel, more or less, right? That's always kind of like a little bit subjective, but then it's very clear that the treatment induces a change. Yeah? So parallel before and then treatment, and then again parallel afterwards. Yeah, because like, of course, this change only affected like 2 years, and then afterwards, everything was business as usual again. Yeah. Okay. There's another assumption that we need, and this is called common support. And this is important, especially for the X variables, right? What we see here is that in the group that gets the treatment, we need to see the potential outcomes in both time periods without treatment for anyone that has this particular characteristics. And the same thing holds in the group that does not receive treatment. Yeah, so common support simply means that we need people with the same characteristic in all 4 subsamples. Yeah, so kind of like non-treated before the treatment, treated before treatment, and then kind of like the same for after treatment. Yeah, so this can of course also be violated. And in our job training example, it would, for instance, be that people that are older than 25, they experience a different time trend than those below. Yeah, so kind of like the growing economy, maybe the people that are a bit older, they benefit more. So the common trends assumption would not hold if I do not account for the age. Yeah. Now I account for the age. I account for this cutoff at 25. Yeah, by putting, for instance, a dummy variable in there. So the parallel trends assumption in principle holds. However, it turns out that our job training program is compulsory for unemployed people that are younger than 25 years. Yeah? And therefore, the common support assumption will not hold because I cannot find any non-participant that is younger than 25 years. Yeah? So I really need people with the same characteristics in all 4 subgroups. Otherwise, this assumption is violated. Okay, the result is that pretty much if you do difference and differences, you can simply identify the average treatment effect on the treated from observed quantities. Yeah, so kind of like here again, we condition on the same X variables all the time. We look at the people after treatment in the treatment group versus before the treatment in the treated group. This is the first difference. And then we do the same difference in the non-treated group. Yeah? You can write it like this, or you simply look at like after treatment in the treated versus non-treated, and the same thing in before treatment, right? It's the same thing. You can write it in both ways. It doesn't matter. Nevertheless, like the important thing is that we can identify this. All these things are observable. That's the really important thing. Okay, that's the result. Now, how do we estimate a difference in difference? Well, I mean, we actually saw that at the very beginning, we can, well, do this, right? Yeah. We replace kind of like the expectation by a sample average. Here, for instance, we would take the sample average after the treatment took place in the treatment group. Yeah? For all the people that have this particular characteristic that are, for instance, in the IT industry. And we could estimate all these quantities like that. However, again, what is much more popular is to use a regression formulation. Yeah? So kind of we write a linear model like this. And here we have, like, let me just quickly explain what we have. We have here an indicator for the treatment group. Yeah? So this thing will be 1 if a particular individual is in the treatment group, for instance, in the state that has a policy change. Yeah? And it's 0 if you are in another state where there's no policy change. Then we have a dummy for the post-treatment group period. Yeah? So kind of like this simply like after treatment, we are in period 1. And then the most important thing is here this interaction term. And the coefficient that we are interested in is this delta 1 here, the coefficient before the interaction term. Yeah, so this dummy variable, this interaction term, is only 1 for people that are in the treatment group and that are observed post-treatment. And yeah, so what is the point of these dummies? This dummy, think of it as a group fixed effect. It takes out all the group differences that are kind of constant. And the time dummy captures all basically the time effects. Yeah? And if you kind of run this regression, it can be shown that your least squares estimator of your interaction term, of the delta 1, is actually again the vanilla difference in difference estimator that we've seen at the very beginning. And again, as we discussed in the first part of the lecture, because you use least squares, you get very easy standard errors and well, actually very easy standard errors. There is actually, that's actually tricky, but we will talk about that in a couple of slides. And again, why do we use regression? Because, well, we can include other covariates. The expression for a difference in difference estimator will then change. So it will not be this nice vanilla different diff estimator anymore, because we have to do these comparisons for particular X variables and then average across X. However, you know, it's still a simple regression. So kind of we assume that the common trends assumption holds when we condition on this X. And then we just run a regression. And again, this is our parameter of interest. Here I say something that is very subtle, actually. Kind of when we assume the common trends assumption in the previous slide, here, for instance, we condition on X. So kind of we assume that condition on an X means really conditioning on any function on X, right? So kind of when we write the model like this, the regression model, we only control for any linear function of X, whereas in this, we also account for any quadratic, cubic, any nonlinear function of X. So this is a subtle difference here. So kind of when we write a model like this and we only use X prime beta 3 and no X squared, then we assume that the common trends assumption holds conditional on linear functions of X. Okay, but that's a subtle point, yeah. Yeah, what you will see most times in the literature is actually this two-way fixed effect specification. And this is nice because typically we have more data than simply 2 time periods. And this is very easy to combine in the regression framework. Yeah, so kind of, let's say we have T1 time periods before the treatment and T2 time periods afterwards. And the treatment takes place before somewhere in between T1 and T1 plus 1. Then you can simply write the model like this. And it looks complicated, but it isn't, actually. There's simply a time effect that captures all the, well, time effects. There's the alpha, which captures like the group-specific effects. We have our linear combination of x, which are necessary to account for, to make this common trends assumption plausible. And we have our interaction term. So the dummy G is only one if you are in the treatment group post-treatment. Yes, and beta is your object of interest. And so here we kind of have groups. We have actually multiple groups, but not all of them are treated. Then within each group, we have a number of individuals, and then we have many time periods. And if you estimate beta by least squares, you're actually basically pooling everything together. You have like the treated group after treatment versus the non-treated groups before treatment, everything together, all the time periods pooled together, all the kind of different groups that are not treated pooled together. Yeah, so there's a lot of pooling going on when you write it like this. And you can make this more granular. You can make like change the specification pretty easily, actually. And you kind of can get more information if you want to, if you have sufficient data. Yeah, so for instance, let's say you want to know whether the treatment effect lasts or whether it wears off over time. Well, you simply do the following. After the treatment, yeah, so from T1 plus 1 to T2, you put all these interaction variables. Yeah? So kind of like D is now really specific. So you see that kind of it's only one if you are in the treated group and you are in this particular time period. Yeah? So you have now many betas. So for instance, beta T1 plus 1 would measure the treatment effect directly after the treatment takes place. Beta T1 plus 2 would be one period after that, and so on. No? And then typically what you see is that the treatment effect is strong at first and then sort of goes down, so that the effect of the treatment kind of vanishes over time. Okay. If you have panel data, everything is pretty much the same. Yeah, you see I made this in red. It's now that simply instead of a group fixed effect, you have an individual fixed effect. Not much of a big change. It's of course a little bit more plausible that the groups, the treatment and control are, comparable, because what is now treatment and control? Treatment and control consists of the same individual. Yeah, it's the same individual after treatment compared with the same individual before treatment. Yeah. And this makes it pretty plausible that treatment and control are comparable because it's the same people. Yeah. Okay. So this is about specification. And finally, some words on the standard errors. Yeah, so I said at first, well, because we use regression, it's very simple to get the standard errors. That's actually not really true, especially if you have like more data available. If you have like lots of pre-treatment data, lots of post-treatment data, and you don't want to pool. Once you pool, it's a little bit less of an issue, but if you do not pool everything together, there may be issues with the standard errors. So Duflo, I mentioned her already today, so she got the Nobel Prize relatively recently. They have like the super influential paper, a ton of citations, where they actually run simply simulations. Yeah? So they show that if you do differences with the usual least square standard errors, then you're underestimating the standard errors, and therefore you find that the treatment is significant far too many times because you kind of underestimate the variation in the treatment. The standard errors are too low. And if you look at the t-statistic, it's the estimator divided by the standard error. The t-statistic will be inflated, and therefore you will find that the treatment is significant in far more cases than the nominal level of 5%, for instance. Yeah? Which is bad, right? You kind of claim there is a treatment effect, whereas in reality, there is no treatment effect. And the source of this actually underestimation of the standard error is that the outcome variables are normally like correlated over time. Yeah. So for instance, unemployment has a strong serial correlation over time. So if I'm unemployed this year, chances are that I'm unemployed next year. Yeah. There is serial correlation across time. And there's also correlation within groups. Yeah. So kind of because certain groups, yeah, for instance, unemployed people that have get a job training, these share characteristics that make a strong correlation within that particular group. So what should we do? We learned already about a particular type of standard error that can take care of like these correlations. And the answer is basically clustering. Yeah. So you should cluster at the level at which the treatment occurs. So for instance, let's say we have data on individuals in equation 7 here, but the clustering, the grouping takes place on the city level because, for instance, there's a city level policy and your data is actually more informative. You have individual level data. So you should compute this equation here for getting the point estimates of your treatment effect. But for computing the standard errors, you should use clustered standard errors on the city level because the treatment takes place on the city level. Yeah, so with that way, you kind of account for serial correlation and you account for correlation within the city, city-specific effects. Okay. Yeah, so how many slides are left? Okay, there are a couple of slides left, but most of them are pictures. So we just continue a little bit. When you read a paper, people go crazy about the parallel trans assumption. Yeah, so kind of you need to make sure that the treated group and the non-treated group would have developed in the same way across time. It had there not been a treatment. Now, there is no way we can directly observe this. There is no way we can directly test this. Now, because we know that the treatment group, these people will get the treatment after period 0, like they will get the treatment. So what would have happened to them without the treatment, we will never be able to observe. So we can never directly test this assumption. Yeah, so however, people try to kind of make this assumption plausible. Yeah, so it's really crucial to the diff and diff. Therefore, let's just provide some evidence that makes it plausible. And the easiest thing is to provide a graph. So we will talk about the test in the next lecture. So, but the first thing is let's plot a graph. So what do? We want to see a graph where before the treatment, let's say we have 10 time periods before the treatment, and before the treatment we see kind of, yeah, okay, there's change in the outcome variable, but everything moves exactly parallel in the treatment and control. And then what we want to see is that after the treatment takes place, so before everything parallel, then the treatment takes place, poof, big change. This is what we want to see. This makes it sort of plausible that had the treatment not been there, they would have simply continued moving in parallel. This is what we want to see. Again, the assumption itself is absolutely untestable because we can never observe what would have happened to the treated without the treatment. And here's a couple of examples from the literature. So here we have two names that we have seen before, David Card and Alan Kruger, two very big names. And they consider changes in the minimum wage in 2 states, New Jersey and Pennsylvania. So, and yeah, they actually look at kind of people that work at McDonald's, for instance, which are subject to the minimum wage changes, and compare 2 states over time. In one state, we get the change of minimum wage. In the other state, we don't get it. So these are the 2 groups. And then we compare before treatment takes place, before the policy change, and after the policy change. And what we sort of see here is that, well, we see a lot of noise. we see actually that the lines move somewhat parallel, right? Yeah. However, kind of like, is it really convincing? I don't know. That's sort of like the subjective part. Huh? You have to kind of convince the reader that it's more or less okay. Huh? Here we see something that is more convincing, right? So kind of here, this is where the treatment takes place. And we really see that kind of this line is very parallel to this line. And then the treatment takes place kind of in between these two periods. And all of a sudden we see kind of a reversal. Before we had like, so that's about gas prices. So these stations had the higher price, and then after this, they reverse. Same here. They're more or less parallel, and after the treatment, there's a reversal in the kind of relationship between the two types. And final example, and here, this is just pure chaos. So this is actually the paper that you will most likely discuss in the next tutorial. This is about the effect of a terrorist attack on basically crime, because like the terrorist attack induces more police doesn't have effect on crime. So that's kind of what they analyze. Yeah, so these are simply examples from the literature. And yeah, that's it for today. See you in the tutorial.